We're going to take a look at the harmonic series. And the harmonic series is the summation from n equals 1 to infinity of 1 over n. So that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. And we want to show that this series diverges. We'll use the integral test. There are other ways to show that this series diverges. Here's what integral test says. Suppose we have a series a sub n, summation from n equals 1 to infinity a sub n, with all a sub n's positive term series. Suppose we can also find a function, so let f of x be a function that satisfies 4 conditions. And what are the conditions? The first condition is that the function is continuous. F is continuous on the interval 1 to infinity. Now, if the series starts at 2, we would readjust this interval and say f is continuous on the interval 2 to infinity, and so on. Number 2, f of x is positive, so positive for x in the interval 1 to infinity. The third condition is that f is decreasing on this interval 1 to infinity. And decreasing means if we graph it, as we move from left to right, the graph drops, or the bigger the x, the smaller the f of x. And the condition number 4, if we take n to be positive integers 1, 2, 3, 4, 5, and so on, if we plug positive integer n into our function, what the function gives us is the nth term of our series a sub n. So if we can find such a function, then the integral test says that the series n equals 1 to infinity a sub n and the improper integral from 1 to infinity of f of x either both converge or both diverge. You cannot have one converging and one diverging. They have to do the same thing. They have to behave the same way. Now, if they both converge, it does not mean they converge to the same value. That the integral test does not say that. So you have to be careful about that, and we'll look at that later on in an example when the integral test converges. So let's go back to our series, the harmonic series. I'll rewrite it right over here, the summation from 1 to infinity 1 over n. Now, if such a function exists, it would have to be 1 over x defined on the interval 1 to infinity. There can't be any other function that would satisfy all 4 conditions. Now we have to check that all 4 conditions are satisfied. This function is not continuous at 0, but 0 is not in the interval, so it is continuous on the interval 1 to infinity. If you take a look at any value of x that we are allowed to plug in, it has to be greater than or equal to 1. 1 over such value will always be positive, so the function is clearly positive on this very same interval 1 to infinity. And condition 3, here is the graph of f of x equal to 1 over x. So it looks something like this on this interval from 1 to infinity. You can see as we move from left to right, the function drops. You can also see that the bigger the x, the smaller the 1 over x. The formal way to describe it would be to take the derivative, and the derivative is minus 1 over x squared, which is negative for any value of x in the interval 1 to infinity. We can include 1 or not include 1. In other words, this function is decreasing on the given interval. And now the last condition, again, is clear. If we take a positive integer n and plug it into the function, we end up with 1 over n, which is the nth term of our series. So now all the four conditions have been satisfied. We can evaluate the improper integral. So the improper integral is from 1 to infinity of 1 over x, and this is equal to natural log of x. We don't need absolute value since all the x's are greater than or equal to 1, and evaluate this from 1 to infinity. Because of infinity, this is the limit. X goes to infinity, ln of x minus ln of 1. Now ln of 1 is 0, and as x goes to infinity, so does ln of x. So this is going to infinity, and therefore the improper integral diverges. And because of that, the harmonic series also diverges, because they have to, the series and the integral behave the same way. And this is by the integral test. And so we have determined that the harmonic series diverges. Now we can also look at it graphically. It's important to take a look at the graph and understand why the series diverges. So here is the graph of f of x equal to 1 over x. And starting at 1 and going all the way to the right, the area under this curve is represented by this improper integral from 1 to infinity of 1 over x dx. We already saw that that is going to infinity. It's not a finite number. Let's relate the series to this area. So if I redraw the graph one more time, it looks like this. And then on the x-axis, mark the positive integers 1, 2, 3, 4, 5, and 6, and draw rectangles like this. So there's our first rectangle, here's a second, here's a third, here's a fourth, here's a fifth. Note that the sum of the, if we keep going forever this way, the area inside all the rectangles is actually larger than the area under the curve f of x equals 1 over x. But when we compute the areas inside each rectangle, we see that the first rectangle has area 1. The second rectangle, because we plug in 2 into the function 1 over x, the width is 1/2. The second rectangle has area 1/2. The third is 1/3, plus a fourth, plus 1/5, and so on. So the area of these rectangles, when we add them up, is precisely the summation from 1 to infinity of 1 over n. This is our series. And by the picture, this area is greater than the area under the curve. That's represented by the improper integral 1 to infinity 1 over x dx. And so since the integral is infinite, since the area under the graph is going to infinity and the sum of the rectangles is actually larger, the areas of rectangles is larger, we conclude that the series